Greetings, everyone. This is Professor Roman. Let's continue our lecture series, Transition to Advanced Mathematics. We've been discussing transfinite sets and their sizes or cardinalities. And we defined a set to be finite if it is equipolant to one of the sets n sub k. N sub k, as you recall, is the set consisting of the natural numbers from 1 to k. Does not include 0. We've also seen that a finite set cannot be equipolant to any of its proper subsets, which makes perfect sense, but we gave a formal proof of that. Now, some mathematicians might actually feel that there's something, let's say, a bit inelegant about the definition of finiteness because of its dependence on the sets n sub k. In 1888, our old friend Richard Dedekind, whom we've spoken of before, proposed an alternative definition of finiteness that doesn't involve those sets. And we've already done half of it, and the definition is that A is Dedekind finite if it's not equipolant to a proper subset of itself. Otherwise, it's Dedekind infinite. Fortunately, the two definitions of finiteness, the one we gave and Dedekind's version, are equivalent. And Corollary 1222, previous result, tells us, as I just mentioned, that finite sets are Dedekind finite. That's what I meant by half of the equivalence is already done for us. It's the converse we need to be concerned about. And one way to prove the converse is to prove that if A is an infinite set, then it's also Dedekind infinite. Well, since A is infinite, we have a theorem, 1215, that tells us there's a subset S of A that is equipolant to the natural numbers. And here it is. I'm starting the index with 1, S1, S2, and so on. This is equipolant to the natural numbers. Now we can define a map that, informally speaking, right shifts the elements of the set S, or right shifts the indices, but doesn't touch anything else. It leaves all the other elements of A that are not in S, leaves them alone. So officially, F maps A to the set A without the element S1, because we're shifting from S1, S1 gets mapped to S2, S2 to S3, and so on. So nothing gets mapped to S1. S1 is not a part of the image of the function. Here's the official definition. F of sk is sk plus 1, that's the right shift, for all k bigger than or equal to 1, and f of x equals x if x is in the set A but not in the subset S. This is pretty easily seen to be a bijection from A to the set A without the element S1. And so A is Dedekind infinite, because this is obviously a proper subset of A. So we can use either form of the definition in our future work, although officially our definition involves the set n sub k. This theorem, by the way, makes it easy to prove that certain sets, such as n, z, q, and r, are infinite, and I'll let you think about that. The shifting technique that we used here, and you can use it in either direction, you can shift right or you can shift left, is a very useful technique, and it's going to come up again in some other results that we're going to prove. We will see pretty soon that there are infinitely many different transfinite cardinal numbers. Or in informal terms, there are infinitely many different sizes of infinite sets. To discuss the smallest of these infinite or transfinite cardinals, we need a little bit of notation. This symbol, and I've written it in large type so you can see all the flourishes and everything. It's very hard to write this by hand, but you can approximate what it looks like anyway. This is pronounced Aleph, A-L-E-P-H, and it's the first letter of several Semitic alphabets, including Phoenician, Hebrew, Aramaic, Syriac, and Arabic alphabets. So it's quite a common letter. It's the first letter in those alphabets. And for us, we'll generally be writing Aleph subscript 0. And this is pronounced Aleph not. Okay. Now we have a definition. A set A is countably infinite if it's equipolant to the natural numbers. So that would include the natural numbers, of course. And the cardinality of a countably infinite set is denoted by Aleph not. A set is countable if it's either finite or countably infinite. Sets that are not countably infinite are said to be uncountable. Unfortunately, some authors define countable to mean countably infinite. So finite sets are not countable. That seems a little odd if you think about the intuitive meaning of the word countable, but that's the way it is. And authors who use this sense of the word countable will say at most countable to indicate either countable or finite. I don't like this terminology, but some of the set theory books that I like very much use this terminology, so I'm not going to say that it's bad terminology. If it's used by set theorists, some set theorists, then I think we have to say it's an alternative. It's just too bad there are two different versions, because that always leads to confusion. Another term, denumerable, is also used to mean countably infinite. I tend to stay away from that term, but it is very common. To me, the definition of countable has the sense of being able to be counted, even if that process never stops. The point is that in theory, you can count every element in the set in the sense that if you're given an element, eventually it will be counted. So the natural numbers are countable because if you're given any natural number, eventually you'll count it, even though in practice you can't count all of the natural numbers. Well, anyway, that's a debate that's less mathematical, what the best use of the word countable is, so we won't worry about that. But this is how we're going to use it. Set is countable if it's either finite or countably infinite. The next theorem is a three-part theorem, and the first part helps us explain why Aleph naught is in fact the smallest infinite cardinal number. And it only helps because we have not yet defined what it means for one cardinal number to be smaller than another. We'll do that later, so not to worry about that now. Here's the theorem. Part 1, every infinite set contains a countably infinite subset. That is in fact a rewording of the earlier result we had, that every infinite set contains a subset equipolant to the natural numbers. So we've already done that. This is just a rewording of that earlier result. Part 2 of the theorem says that every subset of a countable set is countable. Seems reasonable. We already know that every subset of a finite set is finite. Part 3, if A and B are countably infinite sets, then so is their union. So as I said, part 1 is just a rewording of earlier theorem. The proof of part 2 will demonstrate that even simple sounding, intuitively reasonable results about infinite sets can be a little tricky to prove with precision. And that's just the nature of things. You know, this stuff about transfinite cardinality can be at times a little unintuitive. But even when it is intuitive, one has to be really careful not to jump to any conclusions based on intuition. If you did that, you might have concluded that the set of even integers is smaller in cardinality than the set of all integers, and we have already seen that's not the case. So in this area of mathematics, we have to be especially careful about our intuition. Okay, so how do we prove part 2 here? So we let A be a subset of B, where B is countable. We have to show A is countable. There's a few cases we can dispatch right away. Since, as I said, every subset of a finite set is finite, we can assume that B is actually countably infinite. If B is finite, we've already taken care of it. So we can assume that B is countably infinite. And to be clear, that's because if B is finite, we've already done the proof. Okay. There's two kinds of assumptions that you make when proving theorems. For example, if you have to prove a theorem like if M and N have the same parity, then something happens. You can always say, well, we can assume if M and N have opposite parity, then something happens. We can assume that M is even and N is odd because of the symmetry, if there is symmetry. That kind of assumption is one type of assumption, but this is a different type of assumption. We can assume that B is countably infinite. There's no symmetry here. The reason we can assume that B is countably infinite is because we have already taken care of the case when B is finite. So that's a different sense in which we can make an assumption. And that's something you should think about until it's clear in your mind. Okay, so we're going to assume B is countably infinite. A is a subset of B. We have to show it is countable. Well, if A is finite, we're done. So this is again the same kind of assumption. Since we're done with that case, we can assume from this point on that A is infinite. Okay. So what we have is this situation, because we've taken care of all other cases. A is an infinite set. It's contained in B, which is countably infinite, and we need to show that A is countably infinite. Now, it often helps in situations such as this when we're dealing with arbitrary sets that are finite or countably infinite, that we transfer the problem from the arbitrary sets to subsets of the natural numbers. And this is how we can do that. The inclusion map sending A into B is injective. And we can compose that with a bijection from B to N, because B is countably infinite. There is such a bijection. Any bijection will do. That gives us an injection because the composition of injections is injective, from the subset A into the natural numbers. So A is equivalent to the image of this function, which is a subset of n. So A, in other words, is equivalent to an infinite, because A is infinite, to an infinite subset of n. Now we've moved everything into n, and it's sufficient now for us to prove that any infinite subset, which I'll call T, of n is countably infinite. So we've managed to replace the arbitrary set B by the set n of natural numbers. We have something concrete to work with because we know what the elements look like. So we know that n is totally ordered by the usual order. That's a big advantage in moving from B to n. And T, being a subset of n, inherits that total order. So T is also totally ordered by the usual order. That means that the well-ordering principle applies to T, because every non-empty subset of T is a non-empty subset of n, and therefore will have a smallest element. Okay? And by definition of smallest, it's unique. This is going to come in very handy. So to find a bijection from n to t, which will show that t is countably infinite, we can define a function inductively. Remember, we talked about inductive definitions when we talked about the principle of mathematical induction. F of 0 is by definition the smallest, also called minimum, element of t. And in symbols, we'll write it this way: f of 0 equals min of t. Once we have defined f of 0 through f of n minus 1, then since t is an infinite set, if we throw out those values from t, I've called that set t sub n minus 1. It's t minus all of the function values so far. This has got to be non-empty. If it's empty, t would be finite, and that's not true. So we can set f of n to be the smallest member of t sub n. Oops, t sub n minus 1. Okay. In order to show that the function f is a bijection, we'll make an observation first about the nature of this function f. Okay. As I said before, t is totally ordered by the usual order, and so f of 0, that's the minimum value in t, is actually covered by f of 1. Remember the covering relation in a partially ordered set. An element b covers an element a if b is bigger than a and there's nothing in between. So f of 1 is bigger than f of 0 because f of 1 comes by taking the smallest element in t other than f of 0. So I hate to say this, but I'll say it informally. F of 1 is the second smallest element in t. So it covers the smallest element. F of 2 will cover f of 1 for essentially the same reason. To define f of 2, we take the set t, we throw away these two elements, and we take the smallest remaining element. So it's going to cover f of 1. There can't be anything in between, or we would have taken that to be f of 2. So we have this chain of covering. So I'll call this a covering chain. Okay. Just to prove this, suppose it were false. Then there would be a first violation of one of these covering relations. We start from the left and we look for a violation. And let's say that, so then there's a smallest k for which f of k plus 1 doesn't cover the previous f of k, which means there's an element t that fits in between f of k and f of k plus 1. So we have f of 0 covered by f of 1, covered by f of 2, and so on until we hit the first violation. F of k is not covered by f of k plus 1, which means there's something in between. Well, we've made a mistake then. We didn't define f of k plus 1 properly, because remember that f of k plus 1 is defined by taking our set t and throwing away f of 0 through f of k and taking the smallest remaining element. Well, t is a better candidate for that than f of k plus 1 because t is still in the set after we've tossed these out, because f of t is not equal to any of these, because t is not equal to any of these. But t is less than what we picked for f of k plus 1, so we made a mistake. We should have picked t or something even smaller than t if it's available. So that's a contradiction. Okay. And so this is indeed the case. There is, for any n bigger than or equal to 1, there's a covering chain from f of 0 to f of n. Okay, so we're going to need this. This is going to help us prove surjectivity of f. Now we also notice something about the function f. F of 0, of course, is bigger than or equal to 0 because f of 0 is the smallest element in t. That could be 0 if 0 happens to be in t, but doesn't matter. F of 0 is bigger than or equal to 0. Everything's bigger than or equal to 0 because f of 0 is a natural number. And so this chain here implies that f of 1 is bigger than f of 0, which, as we just said, is bigger than or equal to 0, so f of 1 is bigger than or equal to 1. And in general, f of n is bigger than or equal to n for all n. And this is very easily proved by induction. We know p of 0 holds. We just talked about that. If we assume that p of n minus 1 holds, where n is at least 1, then again this covering chain tells us that f of n actually covers f of n minus 1, but all we care about now is that it's bigger than fn minus 1, which by the inductive hypothesis is bigger than or equal to n minus 1, and so f of n is bigger than or equal to n. So we have shown by induction that p of n holds for all n. Speaking generally, any function that maps the natural numbers to the natural numbers and that has the property I called a g, that g of n is bigger than or equal to n for all n, is called an inflationary function. Because, informally speaking, it inflates all the values. If a value stays the same, they consider that to be inflated, even though technically it's not. So when this is a strict inequality, of course, there is a real inflation of the value. G of n is bigger than n. But in any case, this is called an inflationary function. So what we've just proven is that f is inflationary. Now we can get down to the real business. We've got a couple of properties of the function f that we can work with to show that f is bijective. This covering chain business tells us immediately that f is injective, because if we have two different values, two different natural numbers, m and n, we can assume now, because of symmetry, that m is less than n. Then m will have the form n minus k for some k between 1 and n. So if k is 1, this m is just n minus 1. When k goes all the way up to n, m is 0. In any case, we have a full covering chain from f of 0 to f of n. So if we just start that chain at f of m, we have this chain. But remember, these are stronger than strict inequality. They're covering relations, but they are strict inequalities. And so by transitivity, f of m is less than f of n. So if m is less than n, f of m is less than f of n, which tells us that f is injective. As far as surjectivity is concerned, suppose that f was not surjective. Then there would be a smallest element, little t and t, that was not in the image of f. To say that f is not surjective is to say that the image of f is not all of capital T. So there are some elements in capital T that are not images of anything in the domain, so we can take the smallest one. Again, that's by the well-ordering principle. But f is inflationary, and so t is bigger than or equal to f of 0 by definition of f of 0. Remember, it's the smallest member of t. And this is the inflationary part, t less than or equal to f of t. Well, now we've got a big problem, because that means t is one of the elements in this covering chain. Okay. But that's impossible because t is not in the image of f, so it's not of the form f of anything. Okay. So f is surjective and therefore bijective. And that concludes the proof of this part 2 here. Every subset of a countable set is countable. So you can see that it took some effort to construct a proof. And as a matter of fact, I'll tell you that this wasn't the first proof I constructed. I constructed an informal proof, and then I thought, well, you deserve a formal proof. That's the whole point of this course, one of the points. And I wrote a formal proof, and it was mathematically correct, but I didn't really like it that much. It seemed a bit awkward. And that's when it occurred to me that there is this covering relation that was not that difficult to establish, and that might be the best way to approach this proof, a formal proof in this case. Okay. So I had to think about this myself a few times and come up with a few different ideas. Okay. Part 3. If A and B are countably infinite sets, so is their union. So A can be written this way because it's countably infinite. B can be written this way. And we have to show the union is countably infinite. Now, it might occur to you that a proof might be easier to find if A and B were disjoint. And so let's temporarily assume that this is the case, and then deal with the alternative where they're not disjoint afterwards. This is a common approach to things. When you're trying to prove something, you might say, gee, I wish something else was also true. It would help me with the proof. You can assume that that's true, but only temporarily. Construct a proof based on that additional assumption, but don't forget that you then have to erase the additional assumption and get a proof without that assumption. But the proof with the assumption may help you guide you to the right path anyway. Proving theorems is not easy, and you need all the tricks you can find. And sometimes the trick is to assume something that may not be true to help you get an initial proof that will help you see what to do in the general case. So let's assume then that A and B are disjoint. The key idea here is to divide one of the sets into two parts. And we want them both to be infinite, countably infinite parts. So there's one sort of obvious way to do that, and that is to break off the odd-indexed elements and the even-indexed elements. So let B1 be the set of all elements of B that have an odd index, and let B2 be the set of elements of B that have an even index. These two sets are countably infinite, they're disjoint, and their union is B. They are, as you know, a partition. These two sets B1, B2 form a two-block partition of the set B. And you will see in a moment why that's a good idea. We can define two functions, f from A to B1 and g from B to B2. F of AK needs to be an element of B with an odd index, so this is sort of an obvious choice, B sub 2k plus 1. And G needs to take BK, an element of B, and send it to an element of B with even index, so why not B sub 2k? Now, the domains of F and G are still A and B. They're disjoint because we are assuming temporarily that that's the case. And the codomains are now disjoint, B1 and B2. And that's why we did the split, really. So we can take the disjoint union of F and G. We could have done that anyway, but see what the problem would be is that because the images weren't disjoint, we would have some problems with injectivity. But now the disjoint union of F and G map A union B, this is a disjoint union of A and B, to the disjoint union of B1 and B2, which is B. And this is bijective. F and G have nothing to do with each other. Their domains are disjoint, their images are disjoint. Okay. So this is in fact bijective. Therefore, the cardinality of A union B is the cardinality of B, which is all if not. So A union B is countably infinite. And that concludes the proof under that additional assumption we made that A and B are disjoint. So what do we do if A and B are not necessarily disjoint? Well, there's a common technique to replace two non-disjoint sets by two disjoint sets of the same cardinality. For the set A, we replace it by A prime, which is the Cartesian product of A and the singleton set 0. So the elements of A prime are ordered pairs where the second component is 0. We do something similar for B prime, but we make the second components 1. Now 0 and 1 are sort of arbitrary choices. We can put anything here and here as long as they're different, because that makes A prime and B prime disjoint, because they never have the same second components. These sets are countably infinite, and they're disjoint. So our previous work here shows that A prime union B prime is countably infinite. And from that, we have to show that A union B is also countably infinite. And we can do that with a map, a function that sends A union B to A prime union B prime. And for an element of A, we send it to the ordered pair in A prime. So x goes to x comma 0. We can't just take any element in B and call it x and send it to x comma 1, because that element may also be in A, and we've already defined f of that element. So we just take the rest of the elements in B minus A, and we send them to the ordered pair x comma 1. This is an injection. And so, and that I'll let you sort out. And so A is contained in A union B, obviously, and that's equivalent to the image of the function, which is contained in A prime union B prime. I didn't say F was bijective, it's only injective. But A union B is an infinite set because it contains A, which is infinite, countably infinite in particular. And so the image of F is an infinite subset of the countably infinite set A prime union B prime. And part 2 then tells us that the image of F is countable because it's a subset of a countable set. But we already know it's infinite because it's equivalent to A union B, which is infinite, and so it has to be countably infinite. So that's the proof. The proof of this theorem uses a lot of our techniques, a lot of our thought processes involving transfinite sets, and so it's well worth going over until it all seems to make sense. I realize that this material is somewhat abstract, and so it can be a struggle to learn. The only way you can learn it is to think about it long enough for it to begin to make sense. That's your choice, of course. I had to do it when I was a student first learning this material. That's just the natural thing to do, so to speak. Okay. The fact that every infinite set A contains a countably infinite subset has some very interesting consequences, and we can use this shifting idea to explore some of those. So, for example, here's a set A, and here is the subset S that's countably infinite. I've indexed this one now starting at 0 because it turns out to be more convenient. It could have started it at 1, or frankly at any integer, doesn't matter. Now what we can do is define a function. Oh, I've also got two elements, alpha and beta, that are not in the set A. We can define a function from A to the disjoint union of A and the set containing those two extra elements as follows. The elements of A minus S I want to leave alone. I want to fix them. So f of x equals x for x in A minus S. As to the elements in this subset, or sequence if you prefer to call it that, starting with A sub 2, I'm going to shift 2 steps, this time to the left. So A sub k is sent to A sub k minus 2. And this has to be for k bigger than or equal to 2 because you can't have any negative exponents here. Negative indices here. This function, therefore, is not yet defined on A0 and A1. And we can set f so that A0 is sent to alpha and A1 is sent to beta. And that's what you can see in the picture here with the arrows. This is a bijection, and I will leave that for you to explore. So these two sets are equipolant. So in words, if you have an infinite set and you toss in 2 more elements, you don't change the cardinality. You don't change the size of the set. That sounds really weird. Of course, it's not true for finite sets. But you already now, I guess, figured out that the theory of infinite cardinalities is a little weird. Okay? Or weird is obviously not the right word. Counterintuitive is a better word. It's also easy to see how this example can be generalized to any finite set. So what we can do is we can shift, let's say we have a set B that has size at least 1, size n at least 1. We shift n steps to the left rather than just 2 steps. So we send A sub k to A sub k minus n for k bigger than or equal to n. So the picture looks very similar to this, but we, instead of 2 steps, we shift a bunch of steps. For the same reason, really, we have a bijection from A to A union B. So in words, if we have an infinite set, we can throw in any finite number of elements, 50, 100, a billion, will not affect the cardinality of the set. But we can even take this a step further, and that's indicated by this picture. Instead of shifting left, what we're going to do is split the infinite set S into 2 equal infinite parts, just as we did in a previous proof. We can send A0 to a brand new element, alpha 1, A2 to a brand new element, alpha 2, A4 to a brand new element, alpha 3. So we can send the even indexed number elements in S to other elements outside of the set A. And we still have the odd indexed elements that we can send to the full sequence S. A1 goes to A0, A3 goes to A1, and so on. So here are the details on that. the odd indexed elements, a sub 2k plus 1, go to a sub k, this is going to be onto all of S. So what this tells us is that if A is infinite and if B is countably infinite, and A and B are disjoint, even if we toss all the countably infinite elements of B into the set A, bring them into A, we do not increase the cardinality. We don't change the cardinality. So another way to look at this is it's not so easy to add elements to a set, an infinite set, and increase its cardinality. There are ways to get larger cardinalities, as we will see, but it's not going to happen by just tossing in a handful of elements or even countably infinitely many elements. Okay. So here's the summary. If A is an infinite set and B is a countable set, so that's either finite or countably infinite, that's disjoint from A, then the cardinality of the union is equal to the cardinality of A. I didn't have to say disjoint here. Frank, I could have said if A is an infinite set and B is a countable set, then the union has cardinality the same as the cardinality of A. But this is a little bit for emphasis. This is the worst thing you could do to try to, or I should say, it's the best thing you can do to try to enlarge the cardinality, is take disjoint elements and throw them into A. It doesn't do any good to throw the same elements in already because they get discarded, right? Because A is a set, not a multiset. So this is the best effort you can make to increase the cardinality of the set, and it still doesn't work.